Hi everybody. In this video we are going to go over acids, bases, salts, and the pH scale. Now they say there's different types of acids and bases, and technically they're not. All they're really doing is looking at different aspects of a reaction. But the three quote-unquote types are Arrhenius acids and bases, Bronsted-Lowry acids and bases, and Lewis acids and bases. The most commonly used definition for an acid and base would be the Arrhenius ones. An Arrhenius acid is anything that yields hydrogen in an aqueous solution. So here we have hydrochloric acid. You put that in water, it's going to dissociate or come apart. You could also say it's going to ionize. It's going to come apart into ions. You're going to have the hydrogen ion. This is the hydrogen cation. It's technically just a proton floating around. And then you're going to have the chlorine anion. Okay, so this comes apart, makes hydrogen. Great. That's an Arrhenius acid. Another way of describing this is an Arrhenius acid is anything that increases the hydronium concentration in water. So when this hydrochloric acid dissociates, that hydrogen is not just going to sit by itself. It's going to attach itself to unpaired electrons in a water molecule. So this is water, and that oxygen has unpaired electrons here. Well, because that hydrogen lost its electron, it's going to come over here and attach itself to that unpaired electron in the water molecule. That's where you end up with the H3O positive, because you added a proton to this whole molecule. And the water molecule doesn't care. It's still happy. It's got an octet. So that's called hydronium. And acids, when put into water, will increase the hydronium concentration. Now, an Arrhenius base is anything that will yield hydroxide in an aqueous solution. So if you put, for instance here, this example, we have ammonia. And if you add ammonia to water, you're going to get, this is called ammonium. Let's see if I can draw it out. Ammonium. And hydroxide. So how this happens is the ammonia here is going to rip a hydrogen proton off of the water. And so what you end up with is this. So this is the hydrogen proton that kind of got added to the ammonia. That's why it's NH4 plus, and what's left over of the water molecule is the hydroxide anion. And that's why they describe ammonia as being basic when you put it in water. So it's going to either yield hydroxide in aqueous solution, or it can increase the hydroxide concentration in the water. One or the other. In general, when you're looking at Arrhenius acids and bases, Arrhenius acids are going to have something to do with hydrogen. Arrhenius bases are going to have something to do with hydroxide. Looking at the characteristics of these Arrhenius acids and bases, the acids will taste sour, just like citric acid in lemons and limes. They will change blue litmus paper red. They won't do anything to red litmus paper, but if you use blue litmus paper, it will turn red. The bases will taste kind of bitter and or metallic. If you feel them, they'll feel kind of slippery if you rub them between your fingers. And they will change red litmus paper blue. Now, if I were to mix an acid or base, then I would produce salt and water, and that's called neutralization. And neutralization is the reaction of acids and bases that produces water and salts. Now, technically, they'll say the reaction of acids and bases other than water, because water can act as both an acid and a base, and that's why it's amphoteric. So I drew a little equation here. So hydrochloric acid plus sodium hydroxide, or Li, which is, this is an acid, this is a base. When those react and go through a neutralization reaction, you'll end up with table salt, NaCl, plus H2O, plus water. So that's a neutralization reaction. Now, looking at the other definitions of acids and bases. Again, if it's an Arrhenius acid, it's going to be a Bronsted-Lowry acid. It's going to be a Lewis acid. If it's an Arrhenius base, it's going to be a Bronsted-Lowry base and a Lewis base. They're just Bronsted-Lowry and Lewis are looking at Bronsted-Lowry looks at protons, and Lewis bases look at electrons. So the Bronsted-Lowry acids. Bronsted-Lowry acid is anything that donates a proton, and a Bronsted-Lowry base is anything that accepts a proton. So in this equation, if I put hydrochloric acid in water, I'm going to end up with hydronium and chlorine, a chlorine anion. So what donated the proton? Well, the hydrochloric acid did, because it came off. The only thing that came off was the hydrogen cation. Okay, so that little proton popped off, came and hooked onto the water. And that's where you get the hydronium from. So the hydrochloric acid donated the proton. The water, in this case, is the base because it accepted the proton. Okay, so that's the definition of a Bronsted-Lowry acid and base. Lewis acids and bases look at donating electrons and accepting electrons. So a Lewis acid accepts a pair of electrons. A Lewis base donates a pair of electrons. So if we look at, this is basically when you put ammonia in water, it takes that hydrogen proton off. Okay, so the acid is accepting the pair of electrons. So the water technically would be the acid in that part. The Lewis base, the ammonia, is donating the pair of electrons, and that's how you end up with ammonium. Another example would be this. Oh, there we go, acid and base. In this one, you've got the, again, ammonia donating the proton, or donating the electrons. This one is accepting the electrons, and so this is the acid, this is the base. Again, the only real difference between all of them is what aspect of the reaction are you looking at. Okay, so that's kind of the definitions of acids and bases. Salts are the substances that result from a neutralization reaction. Again, you have to mix acids and bases other than water to form an acid, or form a salt. Sorry. Salts can also be considered to be ionic compounds that are usually a mix of metallic ions and non-metallic ions. So, for instance, again, sodium plus chlorine is going to give you sodium chloride. Well, sodium is a metal, chlorine is a non-metal. And so you see a lot of salts made out of a mixture of metallic ions and non-metallic ions. Now, one thing that acids, bases, and salts do pretty good is to ionize. Ionization is the dissociation of acids, bases, and water-soluble salts into charged particles in solution. Dissociation just means it comes apart. And so again, if I put table salt in water, it's going to come apart as sodium cations and chlorine anions. It's ionized. You can see the same thing in if I used hydrochloric acid. If I put that in water, it's going to turn into hydrogen cation, chlorine anion. Yeah. Same would happen with bases too. So ionization is just that dissociation. Now what that can lead to then is the formation of an electrolyte. So electrolytes are solutions that can perform electrolysis. Electrolysis is the passage of electrical currents through a solution. And that solution would have to be an electrolyte. An electrolyte is a solution allowing for electrolysis. Okay, and basically what happens is, let's see if I can draw it. So if I have a solution here, so let's say it's water, okay, and I stick an anode and a cathode in here. Okay, that's why your batteries have plus and minuses. They're anodes and cathodes. To complete this circuit and allow electricity to pass through, you'd have to have something in this water. Water in and of itself is not a good conductor of electricity. But if I were to put some table salt in there, so shake some table salt in there, and I end up, that table salt will dissociate, it'll ionize, again, into, let's put these over here. Let's do it this way. Into chlorine anions and hydrogen cations. And now electricity can pass through because this hydrogen is going to go to that anode. This chlorine anion is going to go to the cathode. And so that's what allows it to conduct electricity through this electrolytic solution. Okay? And so again, electrolytes are anything that allows for electrolysis. Acids, bases, and salts that can dissociate in aqueous solution make pretty good electrolytes. That's one of the reasons why if you're dehydrated, you don't drink pure water. Because though you are losing water through sweat, you're also losing salt. And so you need to replace that salt, those electrolytes. It makes your nerves fire properly. And that's why things like Gatorade taste kind of salty, because it's full of salt. An example of this, again, is hydrochloric acid. Put that in water, you get the hydrogen and the chlorine. This is a pretty strong electrolyte. If you look at this organic molecule, when you put that in water, it will just pop off one little hydrogen. And so this is going to be considered a weak electrolyte because it's not dissociating a lot. Not only that, but if you see the dual arrow there, it means that it's dissociating and then coming back together, going this way and then that way, and then this way and then that way. So it's not creating a lot of electrolytic action. So this is a weak electrolyte. When you tend to see an arrow go one way, this hydrogen and this chlorine are not coming back together. That's what makes that a strong electrolyte. Okay, so now we're going to look at pH. pH stands for the power of hydrogen. Technically, it's the concentration of hydrogen ions in a solution. And really what they're looking at is a ratio of hydrogen cations to hydroxide anions in a solution. So you're going to look at how much hydrogen versus how much hydroxide there is. And the scale of the pH system goes from 1 to 14. At 1, then you have the highest concentration of hydrogens and the lowest concentrations of hydroxides. So 0 to 7, to just slightly under 7, that's going to be considered acidic. Hydrogen concentration would be at 1 molar concentration is what they call it, but the hydroxide would be at a negative 14 molar concentration. And as you go up and get to 7, 7 is where they equal out, and so they kind of cancel each other out. That's neutral. The concentration of both hydrogen and hydroxide are at 10 to the negative 7 molar concentrations. As you go up past 7, though, hydroxide kind of takes over, and that's going to be basic or alkaline. When you get to 14, the hydroxide molar concentration is at 1, and the concentration of hydrogen is at 10 to the negative 14. So it's again just kind of a ratio of how much hydroxide compared to hydrogen. More hydrogen, it's acidic. When they equal, it's neutral. More hydroxide, basic or alkaline. Now the pH scale is pretty important to us for embalming because formaldehyde is rather pH dependent. Formaldehyde works best at pH levels of 7.3 to 7.5. The reason for that is that or that is good for us, maybe I should say, because the normal blood pH is 7.3 to 7.5. Now, the problem with that is that when you die, your body starts to become acidic because though you are dead as a person, your cells are not dead and they're still metabolizing and they're making lactic acid as a byproduct. Normally, you would burn lactic acid off, but your cells aren't going to waste oxygen on burning lactic acid off. So you get this buildup of lactic acid. So your body goes acidic down to about 6 or so. Then that acidic environment starts to create decomposition of soft proteins. And when the soft proteins decompose, that's when you're going to get nitrogen-based waste products, or what we call nitrogenous-based waste products. Those are alkaline. And so after the body goes acidic for a while, it's going to continuously go alkaline as it decomposes. And that can cause some problems for embalming. Because if formaldehyde goes into an acidic environment, it's going to polymerize. Polymerize means to solidify. It means that it's going to start making chains of formaldehyde molecules, and it forms what's called paraformaldehyde. So here's formaldehyde plus acid gives you this complex, paraformaldehyde. And it's actually going to have multiples of this complex. I think the average is 8 of these in a chain to 100 in a chain. That's kind of the average length. Paraformaldehyde is actually used. We do use this in some embalming powders, but we would not want to inject liquid formaldehyde or formaldehyde in a solution, have it go into an acidic environment, and then have it turn into paraformaldehyde. That would cause a pretty big problem in our embalming process. If you put formaldehyde in an alkaline environment or basic environment, it'll actually start to decompose. So not neutralize, that's not the right word, but it will actually fall apart. That process is called the Cannizzaro reaction. What you're going to get, so again, this is formaldehyde here. This is sodium hydroxide, a pretty strong base. What you're going to get out of this is a carboxylic acid salt and an alcohol. That's what they always form. So this is sodium formate, this particular salt, sodium formate, and this is methanol that comes out of it. So again, I don't want my formaldehyde being decomposed. Sodium formate and methanol aren't going to do me any good to embalm a body with. So how do we counteract these pH changes in the body? We use things called buffers. Okay, so that's a buffer right there. Buffers are needed to counteract the pH changes occurring after death. So as I said, the body initially goes acidic. Over time, it's going to become more and more basic. So buffers are capable of neutralizing very small pH changes. Buffers can act as both acids and bases. Thusly, they are amphoteric, right? Some common embalming buffers, in the old days, they used to use borax. So borax you can buy at the store. It's, you use it for laundry, killing ants, it's good for that, but it's a buffer. And in the old days, they would take a little scoop of borax and put it in the embalming machine. We don't use borax much anymore. We tend to use more sodium phosphates and citrates. Citrates are salts of citric acid. Those tend to be used as buffers the most often. All right, so that finishes it up for acids and bases and salts and pH. Next time we're going to talk about radiation.